Hi, my name is Alex Hong, and then I'm the first author and the presenter of this paper, CSAM, a 2.5D cross-slice attention module for anisotropic volumetric medical image segmentation, and we're from UCLA. First, we're going to be introducing what 2D, 3D, and 2.5D segmentation is. So 2D segmentation is pretty simple. So you input the model with a 2D single slice 2D image, and then you use 2D encoder and decoder and get the segmentation results. And for 3D, that's basically the same thing. So you input the model with a 3D volume, and then you use 3D encoder and 3D decoder, and then get the final results from the decoder. And that's in like 3D volume. And 2.5D is less explored, and then that's like loosely defined. So one of our contribution in this work is we gave formal definition of 2.5D segmentation. And then 2.5D segmentation is a little bit more interesting. So because it's essentially input the model with the entire volume, or at least some part of the volume, like consecutive slices, but are only using like 2D encoders and 2D decoders. And we're trying to like incorporate volumetric information either before the encoder, or between the encoder and decoder, or after the decoder. And this work, or like in the most popular 2.5D segmentation methods, we're using incorporating the volumetric or cross-slice information, which is what we call it, in like between the encoder and decoder. And what's the current state in anisotropic volumetric volume segmentation? Like 2D methods clearly have like disadvantages because they don't fully utilize volumetric information. So when doctors or clinicians actually like look at the medical images, they look at the single slice and then they move up and down to incorporate like volumetric information in there. So 2D methods like clearly does not utilize that information. And for 3D methods, they use like the volumetric information, but they're bad at dealing with anisotropic images because the in-plane resolution for medical like images are pretty good, but like the through-plane resolution for medical images are like pretty poor. Can be pretty poor. Like then the resolution between slices. And the 3D methods are bad at dealing with that. And then 2.5D methods, they're like actually better at dealing with anisotropic images, but usually there's like some hyperparameters we need to determine, and like 2.5D methods can have a pretty large memory consumption. So that's what we're trying to solve in this work. So our main contribution is we proposed a formal definition of 2.5D medical image segmentation methods, and you can find more details of that in our paper. And then we propose a new 2.5D cross-slice attention mechanism that can greatly reduce the number of parameters compared with like current state of the art. And the proposed model can be like inserted into any existing 2D methods. And then like experiments have shown that our methods works like really well compared with like other methods. So here's a brief overview. Like I said, we're trying to like do the cross-slice attention in between the encoder and decoder. So all these input feature maps are like the encoded feature maps from the output from the encoder. And then L is the number of slices, and HWC is the height, width, and the number of channels. So each box actually represent like the feature maps from like each slice. So the input feature the feature map go through like semantic attention, positional attention, and slice attention sequentially, and get the refined feature maps. A little bit more details on like each attention module. So semantics attention actually just trying to generate an attention map to that indicates like which channel of like which semantic channel is more important in the segmentation. And then the positional intention is like basically the same thing. We're trying to generate an attention map that tells you like which spatial location, like which spatial position is more important. And the slice attention is just trying to like generate an attention map all over the slices to say like which slices are more likely to contain like important information regarding the segmentation. And then there say slice uncertainty module in the slice attention. So we're trying to what we're trying to do here is because like I said, the in-plane resolutions are pretty poor. I mean the in-plane resolutions are pretty good, but like the information between slices are pretty bad. So we're trying to like incorporate that in the model because there's supposed to be more like uncertainty between slices. So we're trying to like model that with low rank Gaussian distribution. Just defined like that. You can find more details about that in the paper, but the motivation is just trying to because like so what we're trying to do here is trying to sample the attention weights for the slice attention from a multivariate Gaussian distribution, so which is low rank. So the attention of each slice is like more correlated with the attention of slice like nearby. So that kind of makes sense. So this is the implementation of our proposed module on like UNet and UNet++. And that's the ablation study on processual neural segmentation on UNet++. And TZ is transition zone and PZ is peripheral zone on prostate. And then the stars indicates like statistical significance, and the numbers are dice coefficient. So using all three attentions actually like work the best, and then using uncertainty actually works like better than not using uncertainty. So that uncertainty works as kind of like a regularizer. And that's the prostate zonal segmentation results. And our proposed method is comparable to a CatNet, which is the state-of-the-art 2.5D segmentation method that we proposed in the previous paper, but the method proposed in this paper has like a lot less parameters. And that's the result on prostate cancer segmentation. We compare our method with all the 3D methods, and ours works the best. And then that's the dice coefficient, and that's the classification AUC. And the positive case is defined as if there's like one positive pixel in the entire volume, then we assign that to like positives. Then for the visual results, our method, like the green ones are the ground truth and the red are the prediction. So on the bottom, like only our method is able to like pick up like these two lesions. And that's on the left is a cardiac segmentation on a public data set, and on the right is a placenta segmentation. And it's pretty clear that our method works the best on like different backbones compared with like 2D, 3D, and 2.5D methods. And here are the visual results of placenta segmentation. And it's pretty clear that our method works the best because the other methods kind of like under segment a lot of the slices. So in conclusion, our proposed method has the following advantages. It has like minimal additional parameters to train, and then it can be incorporated into like any existing networks. And then our method outperforms all the current 2D, 3D, and 2.5D models, like under simple training and data augmentation settings. And thanks for listening. That's it for the presentation.